All right, so we're going to be digging a little deeper into molecular orbital theory. We talked previously about basic molecular orbital theory, combining 1s or 2s orbitals to make bonding and anti-bonding orbitals, but it gets more complicated when you throw the p-orbitals in as well. So let's go over the objectives for this lecture. So we are going to be looking at explaining the ordering of molecular orbitals in second row molecules. We're not really going to go beyond that. Excuse me, the molecular orbital theory starts to get more complicated than we can really handle in this intro class. We'll draw and fill molecular orbital diagrams of diatomic molecules through the second row and explain how molecular orbital theory creates delocalized orbitals. We won't be very quantitative when we get to these, but we'll show sort of what we mean by delocalized orbitals. Okay, so incorporating the p orbitals into diatomic molecules. So if you just have homonuclear, meaning, you know, N2O2 atoms, then what you get is that the p orbitals that point in the direction of the two nuclei, or you got two nuclei, then there's, if you draw a line between them, there's p orbitals that are pointing that direction. And we just sort of arbitrarily call that the px. We could have called it the pz, you know, it doesn't really matter. Nature doesn't care what variable name you use, but we'll call those the px ones. Those are the ones that are oriented along the line connecting the two molecules. So you get sigma 2p bonding orbitals and anti-bonding orbitals. And again, you add them up by the bonding orbitals are if you take the phases to be in agreement with each other, plus, minus, minus, plus, and the anti-bonding orbitals are if you line them up like that. Again, it's just combinations of the atomic wave functions. One orbital's agreeing, one orbital's disagreeing with the opposite phase, and the orbitals that are perpendicular to the line connecting the two atoms. The 2pz and the 2py also combine to form bonding and anti-bonding orbitals, right? The bonding orbitals have plus, plus, and minus, minus. The anti-bonding combinations will have plus, minus, and minus, plus. And so the bonding ones look like that. The anti-bonding ones look like that. And these are the 2p, the pi 2p and the pi star 2p orbitals. And the same with y, we just give them the same names. They're both pi 2p and pi star 2p because they're completely symmetric. They're degenerate orbitals. They have exactly the same energy. Okay, so those are the p orbitals. We have sigma bonds from the 2px and pi orbitals from the 2py, 2pz. Okay, so this is what the molecular orbital diagram looks like in this case. So there's actually a subtle difference here. Most of these are the same, but there's one difference that I'll show you. So we're looking at the n equals 2 main group elements combined into diatomic molecules, B2, C2, N2, O2, F2, Ne2. You could say, like, I've never seen C2. I mean, you can get C2, it's just not particularly stable compared to other compounds that carbon can make. It's a perfectly, reasonable molecule, just not incredibly stable compared to the other compounds it can make. Okay, so we start with the atomic orbitals, and the atomic orbitals, the S ones behave the way you'd think. You've got two S's combining to sigma 2s and sigma star 2s, and the 2p, remember the 2p orbitals in the atoms are all the same energy, they're degenerate, and then you get the pi 2p orbitals, right? These are the ones from the py and pz. The sigma 2p, that's from the px. Now these are both lower in energy than the p orbitals, and then you've got the pi star 2p and sigma star 2p. Those are both higher in energy than the corresponding orbitals. So we got the atomic orbitals. So if you notice, we got 1, 2, 3, 4, 5, 6, 7, 8. Atomic orbitals, we have 1, 2, 3, 4, 5, 6, 7, 8 molecular orbitals. You have the same number on both sides. So with O2, F2, and E2, those are about the same. The orbitals 2s are the same, but we notice that the 2p ones look a little different. In the case of the smaller atomic number atoms, then the pi orbitals are lower in energy, but in these O2, F2, and E2, then the sigma orbitals are lower in energy. And that is sort of confusing. Again, we're dealing with quantum mechanics here. So some of these subtle energy differences, you have to grind through and do all the calculations. This is just a representation of how they form. Generally, you know, the 2s orbitals will be much lower in energy, but they're not totally lower in energy. There is some mixing between the 2s and 2p, and that's where this comes in.